So this last method, the official name is the shell method. What we have been doing is the disc or the washer method. A disc method would be discs that are solid. The washer method is slices that have holes in their core, in their center. This is the shell method. The advantage of the shell method is it allows you to do a vertical axis, but to stay in X terms and not have to convert everything to Y. So for vertical axes, you have two choices. You can choose, if you like the disc and shell method, you may do that. You just have to remember to convert everything to Y. If you don't want to bother converting everything to Y, then you can use this new method called the shell method. Right, this is just a review. This is the disc or washer method. Okay, so remember, A for alpha stands for that axis of rotation that's horizontal. And so this would be horizontal implies stay in X terms. Whereas vertical, that vertical would imply that we switch to Y terms. And the new one I'm going to show you today is that we can be a vertical axis of rotation, but we can stay in X terms. So that is the advantage of doing a shell method. All right, so here's just what we demonstrated in class. The unwrapping of a roll of toilet paper or butcher paper or paper towels can be converted to a rectangular prism. Sometimes your shells get smaller towards the center. So in this diagram, the outermost shell, it has the biggest radius and the biggest height. But each shell, as you move towards the center of your axis, each shell not only changes its radius, but it can decrease in height too. Then you get this little funnel divot on the inside. So that is possible as well. We can handle both things. We can handle both a changing height and a changing radius. But everything is predicated on the fact that every shell, as it's peeled off, will become a rectangle. All right, so here's how we go. The height is always the Y value, which is f of x. So this is Y, or f of x, which is always the height. And then the length of the base is the circumference, which unwrapped, the circumference will become the length of the base. The area then is the multiplication of the two. So here's the idea, is that we get to stay in X bounds. So these are X terms, which is beautiful. We will be doing the circumference times the height. And then this little dx is what accounts for that third dimension of volume, that very, very paper thin, microscopic amount of depth that it would have. All right, the circumference is 2 pi r. So these two things are the same. The height is y. But we could have more than one y. We could have a y2 minus a y1. So it could be y2 minus y1, or it could be f of x minus g of x. Those are the same thing. That's going to account for the height. R is going to be measured as your x-axis, as the x variable, because R is measured along your x-axis, but we also have to account for where the axis of rotation is positioned. So we keep the 2 pi the same, we kind of pull it out, and then r is x minus beta because we're dealing with a vertical axis. So this is where r turns into, so all of this is the same as the radius. We put absolute values around it in case our radius happens to go in a left direction or a right direction. This helps make our radius always be positive. So this is the formula. It looks crazy, but if you understand where it all comes from, there will be a 2 and a pi, which comes from the circumference. The radius will be x minus beta. Beta is the axis of rotation in a vertical sense. And then the height is always f of x minus g of x. So that's this part, which is measuring the height. And then our dx is measuring the depth. 2 pi r h, and then the depth. 2 pi r, h for the height, and depth. This is called the shell method. And at this point, it's just dropping all of the functions into the right place. Here's another picture of something that's rotated around a vertical axis. And as we peel it out, you're peeling from here to here. That would be the first peel, and it would be the next peel would be a bigger peel, but it would be have a smaller radius, but it's going to be a bigger peel. It's like you're just unwrapping it and unwrapping it, like almost like a piece of twine, and you're working your way down. A peel could be like, oh yeah, they have that nice little one drawn for you there. Okay, it could go like that. And again, what's the advantage? The advantage is we get to stay in x. That's the big advantage. The downside is people forget the absolute values. The downside is people forget the subtraction of both the beta and maybe of the other curves. So let's try setting this up and just see how this is going to work. Here's my region. I'm still approaching it coming from the top down because I'm measuring this in terms of x. All right, my region starts on x at 0, but where does it end on x? So here's the question mark. If we start at 0, where will it end? And you know that the curve is part of a cubic equation and it's intersecting the number 4. So how far do we go? The cube root of 4. All right, so the cube root of 4. Those are our bounds. It'll be 2 pi. The radius is going to be x minus the position of the axis of rotation, which happens to be 0 in this case because we're rotating around the y-axis. And then our upper curve is the number 4. Because it's the horizontal line that forms the upper edge. And then our lower curve is x cubed dx. So that's the setup. I can pull out 2 pi out to the front. Then I have x minus 0. Which is just absolute value of x, and then 4 minus x cubed. If you have your calculator, you'll just hop into Math 9 at this point. If you don't have your calculator, let me show you how to deal with the absolute value. What?
No, I was like, why in the world are we not going 0 to 4, but we're doing it because of x.
We're on the x-axis, right? Okay. All right. The absolute value. You need to look at the original region and just decide, is your original region in a positive quadrant or not in a positive quadrant? Like if our original region would have been this side instead, okay, the other part of it, but our original region is in a positive quadrant. The other way you think of it is any bound between 0 and rad 3/2, those bounds are all going to be positive numbers. And so when I put those positive numbers into here, do I need the absolute value if I'm already plugging in positive numbers? And the answer is no. I don't need the absolute value because the bounds themselves are already positive. So you really got to watch it if your bounds are going to be negative. That would cause you to have a problem. Yeah.
Only the x.
Only the x.
So it doesn't matter if it's 21.
Right. Only the radius. We need the radius to be positive. And so that's the only thing we have to worry about. Okay. So in this case, I don't need the absolute values, so I can remove them. And I would simply have x times 4 minus x cubed, which is a distributing situation. If you have absolute values, you cannot distribute. But if you can remove the absolute values, then you can distribute. This is just the rules of algebra. So you would be allowed then to keep going, and you would have 4x minus x to the 4th dx. And then that's no problem to do without your calculator. But typically they'll let you have your calculator if it's going to be something that would have negative would be a problem. Okay, let's try setting up another one. Okay, here we're going to be bounding, and I drew it out for you, a parabola connected to the line x and rotated around the y-axis again. So if we're going to draw our picture, the rotation's going to swivel like this. And then it's going to look okay. Does that remind anybody of anything? What does it look like to you? A spinning top, maybe? Something you would spin? Yeah. Okay.
What's the Jewish?
A dreidel? Mm-hmm. Yep, something kind of like that. Okay, so this is something that maybe is a spinning top with a pointed edge. You could do this the way you did yesterday, and you could switch everything over to the x terms. That would be fine. So your bounds then would go from 0 to 4, and you would switch everything, you'd switch everything to your y terms, and your bounds would go 0 to 4. Or we can leave it in x terms and set it up with shells. So there will be times where the directions will specify you must do this method to demonstrate you know how to do it, but there will be other questions where like, choose, you could get to choose. So we are going to stick with leaving everything in x terms. All right, so we are going to commit to x terms, which means we need to figure out our bounds. Our bounds are 0 to something. So then we're going to need to do a little algebra to figure out what our bounds are, because we want to figure out when does 4 minus x squared intersect with x. So because that's a quadratic, it would be x squared plus x minus 4. This does not factor nicely. So the only solution I would have if I don't have my calculator, if I can't factor, what's my only other recourse? Okay, so quadratic. So x is going to be -1 plus or minus the square root of 1 minus 4ac, so that'll become plus 16 all over 2. In other words, -1 plus or minus the square root of 17 over 2. So this is an irrational number. I want the positive one because I'm in the first quadrant. If I picked the negative one, I'd be picking the one in the second quadrant. I want the positive one. So my bound, and that's not lovely, is -1 plus the square root of 17 over 2. All right, then I'm going to do shells. 2 pi, absolute value, x minus beta, which is 0 again in this case, because I'm just spinning around the y-axis. And then the upper curve, which is 4 minus x squared, minus the lower function. A lot of times, if you don't get your calculator, the question will be more like, write but do not solve an integral. And so you're like, phew, I don't have to solve it, I just have to set it up. And then they're just looking for you to set up all the pieces. Yeah?
Why is the radius x minus 0?
Okay, good question. All right, then we think about what we need the absolute value or not. Again, we look at our bounds and we think about if I would take any numbers between 0 and that irrational number and plug them in, I'll still have a positive number, which allows me to then remove the absolute value. So the best way to write that is to pull the 2 pi out to the front, give your irrational bounds, and then distribute the number, the variable x. So 4x minus x cubed minus x squared. So that would be if they say write but do not solve, you have it written, you just don't have it solved all the way, which is fine.
Why can't I just leave the one up top?
Leave it
The
as.
equivalent answer.
You can, it just, this might be like matching to the multiple choice. So I just want to show you, the multiple choice probably will not leave the absolute value, so you'd want to know how to do that. But yes, if this was FRQ, they'll take any version of this, in any version that's equivalent, so it doesn't even have to be simplified. Okay, let's try another one. This one I did not draw the picture for you, so you're going to have to draw the picture yourself. This is 3x minus x squared. So tell me what you know about the shape of 3x minus x squared. What kind of parabola? Okay, upside down. What else can you, and so are we just going to draw a random parabola? Does it go through the number 3? Like what? Okay, so how do you want to think of this parabola as what can you factor out in common that it has? X. And then that leaves you with 3 minus x. Those are factors. That helps you sketch the picture. Okay, the picture here is going to be an upside down parabola that goes through 0 and 3 on the x-axis. So we've got 1, 2, 3. So our parabola is looking like this. The parabola is also being intersected by a line that has a slope of, count it, up 1 over 2, up 1 over 2. And so my line is going to look like this. This is the enclosed area of the original region. I'm spinning it around the vertical axis at -2. So this is our first time spinning it around something. So here's the y-axis, but we're spinning it around this, which is a really interesting shape because then your shape is going to look like this. Here's the parabola connected to the, so you're going to get this shape then that looks like that, like this, and like that. So it's kind of like a bundt cake with a slanted side to it. It's definitely got a cavity in the middle. This is the kind of function you really don't want to switch to y. Because if you try and switch y equals 3x minus x squared into y terms, It is so messy. You need the quadratic formula again with a plus or minus. It's really messy. This is ideal to keep in x terms. So we're going to keep, what?
If it's like that where it's like super spread out, is that when you should like know like, oh, I should switch to x terms?
It really has to do with this equation and how easy it would be to get it into y terms. Okay? Like this one is easy to get into y terms, right? If I want to get that in y terms, it's x equals 2y. That's a piece of cake. But to get the other one into y terms would require the quadratic formula, which is very messy. Okay, so this one is best to keep it in x terms. So we're going to say, all right, I'm keeping this in x terms, which means the hardest part is just going to be making sure I have x bounds. So clearly I'm going from 0, but I need to know where these two things intersect each other. That might be the hardest part, is finding your x bounds. So our x bounds are going to be, okay, we got to take 3x minus x squared and equal it to half x. I hate having a fraction. So what quick multiplication could I do to get rid of that fraction? Multiply everything by 2. That'll give me 6x minus 2x squared equals x. That's much better for me to work with. I still do want it set equal to 0. So if I set this equal to 0, I will have 2x squared minus 5x. That's an easy factor job. X and 2x minus 5 is the factors. So x is 0 and 5 over 2. So those are my bounds. 0 to 5 over 2. Oh, yeah. All right, 2 pi. Absolute value, so now I want 2 pi r. My r is x minus, and where's the axis of rotation? So this becomes x plus 2. And then I'm going to do what's forming the upper edge, which is the red parabola. So 3x minus x squared minus what's forming the lower edge, and then dx. So you might pull the 2 pi out. You don't need the absolute value anymore because anything from 0 to pi halves as a bound plugged into x plus 2 will guarantee to be positive, so I don't need that anymore. And then we would have 5 halves x minus x squared if I simplified. You don't have to simplify, but if you're looking to match it, that would be the simplified version. All right, how are we doing? Any questions so far? I was going to show you one more. All right, so the last one would be choose your method. You get to pick rotating it around the line x is 6. So if you've got a square root, so 0, there's your square root, 2, 3, 4. So there's my region. The square root, y equals 0, and the interval 0 to 4. But rotate it around 6. So here's your axis of rotation. So you can choose at this point. The rotation would look something like this. So you're going to have this core missing in the middle. It's going to look like that. So, but you could choose then. You could choose to go, if you wanted to convert everything to y, you absolutely could have. If you wanted to keep everything in x, you absolutely could. It's completely up to you. Just keep in mind, it's your original region. So if you're going to be x, then when you think about it, you'll be piercing it from the top down so that you know which one comes first. If you're gonna be doing it in Y, you'll be piercing it from right to left, and so it's gonna be something different that comes first. So make sure that you've got your terms set correctly and you know the subtraction of how the subtraction is gonna go. In one of them, you're squaring the radius. In the other, you're not. So sometimes that gets mixed up in your mind. Okay, I'm gonna pause.